So what we're going to start by doing is, well, working with the spherical Laplacian and attempting to solve the Schrodinger time-independent equation. Now, just like in 1D, it's impossible to solve without knowing some potential, but we at least can reduce it in order to make the specific case for a certain potential much, much easier to solve. We're going to try to reduce the time-independent Schrodinger equation, cross through Legendre polynomials on the way, then we're going to keep our spherical coordinates and try something spherically symmetric. In fact, as spherically symmetric as you can get, as it's going to be radially symmetric too. So we're going to try a field that's just 1 within the unit sphere, and 0 or infinity can also be an infinite sphere, well, everywhere else. And then we'll convert back to Cartesian coordinates, because sometimes for specific potentials, like if we somehow have an infinite cubic well, where the potential is 0 within a cube and infinity outside of it, just like the infinite square well we worked with a while ago, it's a lot more advantageous to go back to Cartesian than to keep working with the unwieldy radius. Well, it's minus h bar squared. Bugs are driving me crazy, dude. So minus h bar squared over 2m multiplied by the spherical Laplacian. Let's just say this is not going to end well. So we start with the radial component, which is 1 over r squared, partial r squared, partial r again, of the wave function psi. Then you add the theta component, which is partial r of sine theta, partial r theta, of psi, plus 1 over r squared sine squared theta. Dude.
What is the bug?
It just flew past my blackboard. It doesn't matter. I'm ignoring it. And this is just going to be psi. And then, of course, you also have to add the potential, because things get a little bit weird without the potential, as we showed the other day. With 1D coordinates, there is absolutely no particle in 1D that can be free or without potential. So we're gonna add the potential over here, and then that's all going to be equal to some energy state, E psi. Okay, that is the time-independent Schrodinger equation. Now, as we did partially the previous time, we're going to attempt the tried and true method of separation of variables. Hooray. But I promise it's going to lead us to a solution this time. So we do something like this. We split psi into psi 1, which is the radial component, psi 2. Remember, we've already said the time component a long time ago, which is for theta, and psi 3, which is for phi. Now, we're going to plug that in here and see what happens. So we get minus h bar squared over 2m, and when we take partial r of something that can be factored like this, that means that only the r component has the derivative being taken, while the other two are constants with respect to r, and so they just get added on. So you get psi 2, psi 3 standing there in the background over r squared multiplied by, using the chain rule, you get, the product rule, you get r squared psi 1 double prime plus 2r psi 1 single prime divided by, it's not divided by anything yet. So you add this to 1 over r squared sine theta partial theta of sine theta partial theta psi. And so when you plug that in, you get r squared sine theta of all the non-angular components. And you get what? Sine theta multiplied by partial theta squared of psi, which is going to be, in this case, partial 2 double prime, psi 2 double prime, plus psi 2 single prime cosine theta. Now, these trigonometric parts are going to be pretty useful later. And then finally, you get plus 1 over r squared sine squared theta partial partial phi squared of psi, which is just going to be all the non-psi components gathered here, while the psi component has a double derivative. Plus u psi is equal to e psi. I didn't plan for writing this low. I wish we could switch to the whiteboard at this stage, but unfortunately this is maybe 20% of the work we need to do. So we erase the upper part of the board and keep going. So what do? Well, I mean, the tried and true method here is just dividing by psi 1, psi 2, psi 3. So what happens there? Well, this gives you minus h bar squared over 2m, and anyone with some sense will also see that you have to multiply by r squared to get rid of this nasty factor. So we multiply both sides by r squared as well, and so in the end we're multiplying both sides by this, and what do we get? Well, we get r squared psi 1 double prime plus 2r psi 1 single prime over psi 1. And then, oh wait, that's not where the parentheses close. Plus, what's this going to be? Well, these two get canceled out, and you get psi 2 double prime sine theta plus psi 2 single prime cos theta over psi 2. And then you take this component and you get plus, well, that's actually pretty simple, psi 3 double prime over r squared sine squared theta. Oh, that should be here. Psi 3. So things are clearly getting difficult. And I'm going to bring this over to give plus ur r squared minus e r squared is equal to 0. And now you might recognize that there are some terms that are a function of only r, and we can separate them from the rest, which are a function of only theta and phi. Yeah, that's still loading. I think it's going to crash. So, first of all, we're going to get rid of this nasty guy that's encircling everything. So, we're going to multiply both sides by minus 2m over h bar squared, which is going to exactly cancel that out, and that gives us. Then we're going to isolate everything that's just a function of r on this side. Over, sorry, this would be single prime. And that is going to be multiplied by this right here. Plus, or rather minus, 2m r squared over h bar squared. U of r minus e. And e is a scalar, so no need to worry. And that is going to be equal to the rest, which is minus psi 2 double prime sine theta plus psi 2 prime cosine theta over psi 2 sine theta plus psi 3 double prime over, that should be there, sine squared theta psi 3. Alright, and now you'll notice this is a function of r, and this is a function of theta and psi, and so both of them have to be equal to some separation constant. In this case, because of something known as the Legendre differential equation, I'm going to set this, and you'll see that very shortly, to L times L plus 1 for whatever L. And this is also going to be L times L plus 1, of course. So now, what do we do from there? Can't have that break. Okay, that works. So, what do we do from here? Well, first of all, we're going to look at this guy because it looks nice, especially because it looks like this term is almost entirely phi, while this term is almost entirely, well, it is entirely theta. So what we can do is we can set minus psi 2 double prime sine theta plus psi 2 single prime cosine theta divided by psi 2 sine theta plus psi 3 double prime over sine squared theta psi 3. That's all equal to L times L plus 1. We now are going to get rid of this part of the phi term by multiplying everything by sine squared theta. And that's going to give us minus psi 2 double prime of sine squared theta plus psi 2 single prime of sine theta cosine theta. Remember, there's a sine theta on the denominator. It gets canceled out now over psi 2. That is entirely theta. And we can also bring this over because this is now entirely theta as well. Is equal to minus psi 3 double prime over psi 3, which is entirely phi. Okay, so it looks like we can term this another separation constant. So we're going to set this to m squared, and we're also going to set this to m squared, mostly because due to the way that phi acts, and the fact that, you know, after completing an angle of 2 pi, phi should loop in on itself, theoretically, psi 3 of some number should be exactly equal to it plus that rotation of 2 pi. And so, oh, that should have been a multiplication, whatever. And so, this is already pretty simple to solve, right? Because you just get minus psi 3 prime prime is equal to m squared psi 3. Hence, if you let psi 3 be equal to e to the RT, or in this case phi, then you get m squared is equal to minus r squared, which implies that, well, r is equal to im. Not that hard. Is it actually equal to negative im because m is equal to ir? Yeah. So r is equal to minus im. And that implies that psi 3 is equal to e to the minus im phi. Very simple. And so now, because of the fact that this should be equal to e to the minus im psi plus 2 pi, m must be an integer, because otherwise 2 pi mi isn't equal to, because otherwise this is not equal to 1. Alright, so we now know that this has to be an integer, which is cool, but that doesn't help us solve that behemoth. Well, actually it kind of does. So let's first erase this. M has to be an integer, not just m squared. That disallows a lot of things. So this equation at first looks like it's going to kill us all. And we give up. That's it, think you're... No, I'm just kidding. So we substitute in, let's call it, I don't know, u. That's what we usually use for a substitution, is equal to, let's go cosine theta, even though sine theta would have almost the same effect. Now keep in mind that since sine squared theta plus cosine squared theta is equal to 1, that means that cosine theta is equal to the square root of 1 minus sine squared theta, and vice versa. I should have worked otherwise. So what happens when you plug that in? You get minus psi 2 double prime. This is just going to be 1 minus u squared plus psi 2 prime u times the square root of 1 minus u squared minus L times L plus 1 psi 2 1 minus u squared is equal to m squared psi 2. And here's the coincidence. This is what we call the generalized Legendre equation. And it's solved by what we call the generalized Legendre polynomial. Now, that's only defined when m is an integer. But, thankfully, we proved that m has to be an integer for this to work. And this also only works when L is an integer, so just keep that one in mind. So, this is related to the standard Legendre polynomial by a factor of, actually I can't remember, but I believe it was the square root of 1 minus x squared to the absolute value of m multiplied by the nth derivative up to an absolute value of the nth Legendre polynomial. Where this guy is the guy we saw a very long time ago, not that long ago, when we were talking about orthogonal polynomials over the space minus 1 to 1. There's an alternative sequential definition of them, but we won't be using that for now. And so that means that this is actually solved by an entirely elementary function, because the answer is just PL of m. Remember, this is going to be a solution in terms of u. It's just this, a generalized Legendre polynomial of u. So plugging back in, that's the generalized Legendre polynomial of cosine theta. There, bada boom, bada bing. We solved that. And so we're still not done, because we have to get to work on that one. And this one is the tricky part, because it's determined by the potential. So, actually, let's do it sure. I hate that bug. It's been pestering me since the lecture started. So we unfortunately erase all of our hard-earned work, but I'll write our solution so far down. So psi 2 is equal to a generalized Legendre polynomial of cosine theta. Psi 3 is equal to e to the minus im phi. Psi 1 is still unknown. So what do we do? Well, the most important order of business is to transfer it from the blackboard to the whiteboard. So we get to r squared psi 1 double prime plus 2r psi 1 single prime over psi 1 minus 2mr squared over h bar squared. ur minus e has to be equal to L times L plus 1. And things are now looking real scary here. So what do we do? Well, of course, we first try to multiply both sides by psi 1. And hey, wait a minute. This is almost the exact same as the regular 1D Schrodinger equation, except we now have this hellish term over here to bother us. So, what do we do? Well, we can't solve this or simplify it any further without an example potential. So let's try an example potential. I'm not going to do the cubic potential today because we're already probably way over time, but let's do the spherical web. So we have u of r is equal to 0 when r is less than or equal to, let's say 1. 1 is a nice number. And infinity anywhere else. Now, you have to think, as u of r approaches infinity, psi 1 is going to have to approach 0. So it looks like, and already, you can think in classical terms that if u is infinity, the force is infinity. So there's something that has to force it right into this spherical well where it cannot escape. So now what happens if we plug this in for r is less than or equal to 1? Well, we get within this spherical shell, and you might ask, well, why don't you do something where the entirety of R3 has zero potential, the free particle? Well, I mean, we already talked about how a free particle in 1D acts, and it was a little bit complicated, so we'll get to that in 3D in a while. Right now, we'll just be doing the spherical well. So this gives us minus 2mr squared over h bar squared. And despite everything, this is at the end of the day just a constant multiplied by r squared times ur, and we set that to 0 in the sphere, minus e. So this is going to be plus e, which is again another constant that can be absorbed into the massive constants. Psi of 1, and so, oh, wait a second, this is actually going to be, well, never mind. And this is going to be equal to L times L plus 1 psi of 1. And so this is going to get mashed into this. And we now have a tough nonlinear differential equation to solve. No, there shouldn't be two parentheses around that. And, no, there should be two parentheses around that. That's not a parenthesis. And once we have this nonlinear homogeneous equation, well, the conclusion of this will be saved for next time, along with the cubical well that I failed to deliver today. Sorry, guys.